Welcome everyone to the second lecture in the Microsoft Research Indian Institute of Science AI seminar series. I'm delighted to introduce Tom Mitchell today, who will be talking on where on earth is AI headed. Now, Tom is the Founders University Professor at Carnegie Mellon, and he's one of the original machine learning pioneers, and he has a string of firsts to his name, including starting some of the first major international conferences and journals on machine learning, as well as starting the world's first ever machine learning department at Carnegie Mellon, which has produced some of the finest thinkers, researchers, and engineers in the space of machine learning. And of course, Tom has himself graduated stars such as Sebastian Thrun and Oren Etzioni, and I know he's had a profound impact also on Thorsten Jokins. Tom is an elected member of the US National Academy of Engineering, of the American Academy of Arts and Sciences. He's a former president of the AAAI, and he's testified on numerous occasions to the US Congress, chaired committees of the US National Academy of Sciences, and he's also advised many companies on their AI strategy. Now, Tom once told me that he never goes to bed without first thinking of or starting a new experiment. And I think this curiosity and this desire to learn and grow is what has led him to make such highly impactful contributions in diverse areas, ranging from never-ending language learning to brain fMRI, and from theory to algorithms to applications. And this has led to numerous awards in terms of the IJCAI Computers and Thought Award, the ICML Best Tenure Paper Award, and so on. Now, in addition to all of his technical accomplishments, I think Tom is one of the nicest, most generous and kindest people in the area. And he's mentored many of us here in India, for which I'm particularly grateful. In fact, one of the most amazing things about Tom is that he started his career flipping burgers in McDonald's. And once they realized that, hey, this guy can do math, they promoted him to the cash register. And there's been no looking back after that, right? As they say, the rest is history. So I'm delighted to welcome Tom. But before we get started, a quick note on logistics. So we've reserved 1.5 hours for Tom's talk. So there should be plenty of time for Q&A afterwards. So if you have a clarification question, or if you have any questions, actually, just type them into the chat. And if it's a clarification question, Tom can take it during the talk, or if it's a discussion question, he can take it afterwards. And helping Tom today and helping him choose your questions and ask them on your behalf, we have a team of moderators, including Bill Thies and Amit Sharma from MSR India, and Partha Pratim Talukdar from the Indian Institute of Science and Google Research. And of course, we also have Akshay Nambi and Venkat Padmanabhan from the previous session. So with that, Tom, thank you so much for being with us here today, and over to you.
Thank you so much, Manik. And I have to admire the ability, your memory ability, because some of those facts that you revealed were shared with you quite a while ago in an informal conversation. So I admire your memory. And thank you for such a gracious introduction. What I want to do today is kind of the opposite of what I usually do when I give a talk. You know, usually I'll have some algorithm or some idea, like how to use unlabeled data and multiple classifiers to estimate accuracy, and I'll go into deeper and deeper detail about a particular approach. Today, I thought what would be interesting is the other extreme. You know, we've all been immersed in an amazing explosion of AI progress over the past 10, 15 years now. And I thought what would be fun would be to look at that much more broadly, see where it's, make some remarks about where I think it has been, and importantly, where it might be going, and then use that as the basis for what I hope will be a very interactive discussion after the talk. So that's the plan. So let's get started. Of course, we should start by looking at where we have been. And over the past 10 years, 15 years, it's easy to see that computer vision, which is an important part of AI, has gone from being really not very competent to being, in some cases, even better at humans. at doing things like finding objects in scenes. Similarly, in speech recognition, when the iPhone came out around 2007, 15 years ago, you couldn't talk to the iPhone. We don't even, half of us don't even remember what it's like to not be able to speak to your intelligent agent in your iPhone. But again, over the past decade, we've seen tremendous progress up to the level where computers can now transcribe spoken language to the equivalent text stream just as well as humans. They don't understand that language as well as humans, but they can go from speech to the words that were spoken just as well. In the area of game playing, we've seen tremendous progress where, for example, AI beat the world's top Go player, the world's top poker players. And this is interesting because it's a different kind of intelligence from computer vision or speech recognition. Those two, vision and speech, are examples of perceptual abilities that happen really automatically and sub-second in our brain. They're what some people call fast thinking, instant reactions. Game playing, on the other hand, strategic reasoning, is a very different kind of intelligence, slow thinking, that requires multiple steps, chaining ahead, thinking, well, if I do this and my opponent does that, then I could do this, but then they'll do that. And you have to think about things much more deliberately, much more consciously. And again, there we've seen tremendous progress. And of course, in the area of robots, we've seen tremendous progress. We're starting to see, for example, autonomous vehicles, self-driving cars starting to drive on some of our highways. So it's interesting that we've seen progress in all these different areas, but of course, there's a common cause to these, the same factors at work in these different areas of progress in AI. It's machine learning, and to a large degree, deep learning algorithms that have made it possible for AI to make this kind of progress in so many areas. Now, that's kind of a quick glance just to set the context on the last decade or so. But I want to point out that this rate of progress is not slowing down. In fact, in just the last few years, there have been several very interesting and important trends for the field. One of them has to do with training and then reusing large deep network models. This started in the area of computer vision, where by, I think, 2015, we were seeing that there were large trained models that had been trained on a data set called ImageNet, which had a lot of photographs labeled by hands, like the ones we saw on the previous slide. But then those models could be downloaded and used by other researchers and developers for other things. And so, for example, this slide shows an example involving skin cancer diagnosis, where a model was trained to look at the blemishes on your skin and diagnose those as cancerous or not. And the interesting thing about this from an AI point of view is that first, this model was trained on over 1 million standard photographs, not photographs of skin blemishes, but those ImageNet photographs that had pictures of things like antelopes and lemons that I showed in the previous screen. Nothing to do with skin cancer. But those models had learned enough about the lighting characteristics of images, what kinds of low-level edge and contour features should be decoded from the raw pixels, etc. And so those models were actually a great starting point for training skin cancer model. And so that model that was developed on over 1 million standard photographs was then retrained using only 250,000 skin cancer images labeled as cancerous or not and which kind. And in the end, that led to a computer vision model that was as good as doctors in terms of being able to look at a new blemish and diagnose it as cancerous or not. So this was a really important development in machine learning, started out in computer vision, but then it has, with a vengeance, moved on to natural language, where we're seeing the same phenomena. And we see systems now that are trained, systems like BERT. Actually, every major tech company now seems to have at least one of these. Google first came out with BERT, but then Microsoft now has Turing and LG, and other companies have other versions. But these are models that are trained on just text that's not labeled by a human, but in a way, it's self-labeled, because the task that these models are trained to do is simply to predict the next word. So given any kind of collection of text, it's easy to mask out a word, show the previous words, and have the model trained to predict the next word. In fact, you can also mask out not just the last word, but words in the middle, which some of these models do. But the point is that these models turn out to be surprisingly useful, at least to me. I never saw this coming, and many of my friends I've talked to never saw this coming. But it turns out once you train these models, not only are they pretty decent at predicting the next word in the sentence, but you can now use those to pre-process any text in order to do a large range of natural language processing tasks, ranging from question answering to labeling parts of speech, which of these words are nouns and verbs and adjectives, to predicting not just the next word, but a whole paragraph of text that may come from this. And so I want to just show a couple quick examples of recent uses of these pre-trained language models. One of my favorites has to do with common sense. One of the age-old problems in AI has been how everybody agrees that common sense knowledge is essential to human intelligence. And one of the questions in AI has always been, how are we going to get all this common sense into a knowledge base so that AI systems can use it? Well, it turns out these language models, simply because they're learning the sequences of words that occur, have implicit in the billions of trained parameters a large amount of information that's relevant to common sense. And so this slide, for example, shows some work by Ye-Jin Choi at the University of Washington, who's developed a system with a nice web demo, if you want to try it out yourself, where you can type in a sentence like Tom lectured at the NASA virtual retreat, and it will then type out a number of natural language phrases that correspond to different kinds of common sense. So for example, if you type in this sentence, it will say, well, that's because person X, that's Tom in this case, that's because Tom wanted, and it will say, to share knowledge or to teach others. But then a different kind of common sense. Before Tom could do this, Tom needed to prepare for the lecture, to prepare for the talk. As a result, Tom feels good about themselves. As a result, person X reasons that Tom could be a professor at the university. Now notice none of these things were actually mentioned explicitly or in any way in the input sentence. But this model that Ye-Jin Choi developed is able to output these kinds of common sense phrases for literally any sentence that you input that describes some event. So that's what I mean when I say these models are surprisingly effective at tasks for which they weren't directly trained. Now, these models tend to be trained on very large volumes of text. Here's an example. Google's latest Palm model is trained on 780 billion tokens of text. The different tasks on which they evaluated are very diverse. The common sense reasoning to natural language inference. Here's an example from the Google paper to show you kind of where things are right now. At this point, you can take one of these trained models, in this case it's the Palm model, which was recently in the last few months released, and you can input a question and try to get an answer. In fact, the way you set up the task of question asking for the model, remember the model is just trained to keep predicting the next word in a sequence. So the way you set up this task is you literally give it this kind of sequence of words where you say, Q, Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? And then you continue and you say A colon, the answer is 11. You can give maybe a dozen such examples of questions, of arithmetic questions and their answers. And then you can input your own, then you can input as the rest of the input, just a question and then the A colon, and let the model predict what will be the next words. Now, interestingly, this is an example that fails. The answer is not 50. But interestingly, they report in the paper that if instead of inputting just the questions with the raw answer, if instead you input the question with an answer that reasons through the chain of thought. So if you set up the context with a question, and instead of saying the answer is 11, if you say answer Roger started with 5 balls, 2 cans of 3 tennis balls, each is 6 tennis balls, 5 plus 6 is 11, the answer is 11, then that's sufficient to make it, when you input your question, to get the right answer. And furthermore, to prompt it, it's sufficient to prompt it to output its own chain of analogous reasoning about cafeteria had 23 apples and used 20, etc. Okay. So again, this is not a talk about language models, but I just want to quickly summarize the state of the art on some of these systems. These same models are now beginning to write code. For example, on the right here is an example where the input prompt is literally a comment string that says, given a string representing musical notes, parse the string, compute the total length of music in beats. It gives the legend. And the output of the model is literally this Python code, which will compute that. So these models are now being trained on a blend of text and code, and it's being discovered that to some degree they can translate literally text to code in simple cases. They can summarize complex patterns. This is an example from a GPT-3, which has some nice examples online you can look at. But one of its uses is you give it a paragraph of text and you ask it to summarize this for a 2nd grade student, and it does. Okay, so you get the idea. Things are moving quickly in this area. Beyond language modeling, we're starting to see the use of deep networks for a variety of ways to support basic science. One of the most visible recent results here is the AlphaFold system from DeepMind, which does the best job so far of predicting the three-dimensional structure of how a protein will fold given just its chemical description, just its atomic descriptions, its sequence. And here you see, I won't go into the details, but these light blue bars are the error rates of the previous state-of-the-art models, and this is the error rate for AlphaFold. One of the interesting things about AlphaFold as a case study is that it is one of the first deep network models that ingests background knowledge about physics and biology as part of its solution. And this is another trend that we're seeing in very recently in deep networks, is a trend toward trying to find ways to train these networks where we can input background knowledge about, in this case, biology and physics, but depending on the application, of course, lots of other kinds of background knowledge. As part of this, we're also starting to see that data that was collected previously for one purpose can sometimes be used for another purpose. This slide shows an example where data that was collected on retinal images, the part of your eye where the photons hit and it gets converted to neural signals, that data that was collected originally for doing diagnosis of eye problems, it turns out can be used, surprisingly, to detect, for example, the age of the person within 3 years. It can be used to detect whether they are a smoker, what their systolic blood pressure is within 11 points, whether they're female or male, and whether they've had a heart attack. So this is an interesting example too, because it highlights the fact that data collected for one purpose and maybe privacy considerations that were considered at the time might become out of date as the technology progresses, and we discover that from that same data we can discover new things. A colleague of mine, Leila Webby, is just in the midst of sending a final copy of a paper to Nature that shows that images of fMRI images of brain activity, which were collected from anonymous, well, from people where the data was then anonymized, that data can in fact now be used to detect, oh, this person in this experiment is the same as this person in this other experiment. So there's another example of technology progressing to the point where we can get new information that we didn't realize we were going to be able to get from old data. We're also starting to see all kinds of work. I think a summary statement for computer perception and AI is that we're seeing superhuman perception in many ways. Some of it has to do with specialized perception, skin cancer diagnosis, but part of it is also just a change in the physics. This paper shows, for example, the ability to look around corners. Here's the sensor, here's an object being sensed behind a wall. But by looking at just the reflection of light off this sidewall, it's possible to reconstruct what was this view, and here's the reconstruction that's made just from the scattered light off the white wall, despite the black wall being between the camera and the object. So when you start combining these new technologies for sensing with deep networks and new technologies for perception, I think we're well on our way to a world where superhuman perception is feasible in specific cases, and in some sense already here. Okay, so much for where we are today. It's always fun to speculate on what's coming next. Of course, nobody knows the answer to that, including me, but we all have opinions, and I think it's fun and useful to talk about those opinions, recognizing that, of course, we could be wrong. So let's see. If we're going to start trying to understand what's coming next, I think it's really useful to look at what are the technical trends. We've been kind of doing that in the last few slides. Rapid progress in natural language. One that I didn't mention, but which I think is really important, is the rise of conversational interfaces. Systems like Alexa, Amazon's conversational interface. I just turned on mine. And superhuman perception, large-scale self-supervised learning. Alexa, stop. Like the kind that's used to train these language models. We're also seeing a big bump in research on how to get humans in the loop with AI systems, including how to make more AI systems that can do a better job of explaining their outputs and can be more transparent. So these are some of the technical trends that I think we're going to see continue over the next 5 and 10 years, and probably even accelerate. So I list these 5 as examples of ones where I think there will be even more research in these 5 areas and some others than there was, say, 5 years ago. So there's some of the trends. But then it's also interesting to look at what are the drivers and governors that are outside of AI. One is just the huge amount of money coming into AI. Microsoft, Google, Facebook, many other companies are investing. And this has caused a sea change in the past decade where we've gone, say in the US, from a situation where most of the research in AI had been originally funded by the government and took place at universities, to today where really most of the research takes place in companies and is funded privately. So it's a different world. That'll surely influence the future of AI. Commodity hardware, GPUs famously have, which were developed as hardware to support gaming systems, have famously become the workhorse for deep learning. And now new hardware being designed that's even more efficient for neural network style computations. Bias and fairness are social issues that have come up that are certainly going to guide and drive the future of AI. Blockchain, many of my friends think blockchain is going to be a big impact. I don't fully understand their reasoning on that, but they could be right. Maybe the rise of the metaverse, the idea of having virtual reality, mixed reality systems. The importance of AI for national defense and therefore leading to international competition is certainly going to color the development of AI, as will privacy concerns. So that's kind of a useful starting point for thinking about the future. One way to get a signal about what some people think the future holds is to look at a collection of $20 million research centers that the US government has funded in the last 2 years and planning to fund this year. Here are the names of these centers and the areas. So there's some interesting trends here. One is these centers are dominated by application-driven centers. So AI in education, AI in agriculture, AI for molecular discovery, AI and next generation food systems. So much of the bet that the US funding agencies are placing on AI many of those bets are centered around specific applications of AI in different fields. And I think that's actually a good bet, because for many years, much of AI research has progressed by really trying to do particular applications, seeing how that fails, and then extending the technology. Another thing to notice in this list is that there are several topics, for example, AI in education, where each year there's a new $20 million center being created. So these are very big bets. This is literally a $60 million set of centers around AI in education. This is an area where I'd be happy to talk more, but not before the discussion period. This AI in online education is an area that I'm very bullish about, and I'm doing some work with some online education companies to see how can we use machine learning together with the recorded log data of literally millions of online students. How can we learn from that data how to teach better the next student? So education is one of those areas. Agriculture is also another area where each year there's a new $20 million center. So anyway, these I think are revealing hints about where some people think AI is going to be highly important. But what'll be the next game-changing technologies? Well, again, nobody knows for sure, but here are a couple ideas. I think one possibility for the next 5 years, maybe 10, is that computers might surpass humans at perceiving human emotions. This slide is from a company called Affectiva that basically develops and markets software that will look at your face and judge your reaction. Now, we have seen in the past decade computers going from not being very good at computer vision to being able to recognize a variety of physical objects and distinguish between cancerous, non-cancerous lesions, things like that. There's nothing in principle, it seems to me, that would prevent computers from also becoming good at emotion detection. And if that were to happen, I think that would be a game changer. You could imagine wearing those, a newer version of the virtual reality glasses that when you're walking around at a party, reveals to you the reactions of the 4 people who just heard your joke that was a little, maybe not as funny as you thought. But there's one technology that I think could happen. What are some others? I think if we had a breakthrough in privacy-preserving technologies, this would be a game changer. Right now, many of the uses of AI that could be used, like applying AI to huge amounts of medical data, are really bottlenecked. The reason we're not doing that has to do with privacy issues. And if we had a breakthrough in privacy-preserving technologies, that would be a game changer. What about a technology that makes device theft impossible? In many cities now, including here in Pittsburgh where I am, there are bicycles just around on the streets. You can pick up one of them, scan your app on your phone to the bike and start riding it. And nobody worries about these bikes being stolen. In fact, the bikes are not stolen. Similarly for scooters, they're around and they're not being stolen. Why not? Well, they have GPS sensors in them, they have connectivity, and so if anybody tried to steal them, we would know where the bike or the scooter was. Similarly, if you buy a high-end car these days, if you buy an Audi or Mercedes, they know where they are. They're in contact with the home station. And so it's harder and harder to steal those cars because the car knows where it is, it can report you. So if we extrapolate this, maybe we'll get to how much can we miniaturize and drop the cost of that kind of technology. If we can, that would again be a game changer. One obvious one, especially given the rate of progress in natural language, even though today's technology is still far from being able to read and understand the morning newspaper, what if computers did get to the point where they could do that and build you a summary of that morning newspaper and then have a discussion with you about that news item over breakfast? If computers get to that point, that'll be a game changer, partly because for the last 25 years, since the advent of the web, us humans have been preparing for that day by typing in all kinds of text into computers so that once they can read, it'll all be there for them to read. And they will, of course, outread us by a factor of 10 to the 9th because we can't read all that stuff, but they will. Here's another, quantum computers. If quantum computers work, that'll be a game changer. Many difficult to solve computational problems will look very different. One of my favorites is, what if computers become programmable by everybody? Toby Lee, one of our recent PhD graduates from CMU, recently did a project for his thesis where he took a mobile device and he changed the conversational interface, and he made it possible for you, the user, to teach new commands to the phone with a combination of conversation and gestures demonstration. So for example, with Toby's system, you could say, whenever I'm driving home after work and I pass the Starbucks, if it's hot outside, order me an iced cappuccino, otherwise a regular latte. And the phone responds by saying, I don't understand, do you want to teach me? And then you can say yes. And you can say, for example, if you want to know if it's hot outside, open this weather app and you tap on it. And you say, here where it says current temperature, if that number is above 80 degrees, it's hot. And then if you want to order the coffee, open this Starbucks app and you tap the Starbucks app. And then you demonstrate and explain how to order an iced coffee. So that kind of programmability by changing our world. Basically what Toby's work is an attempt to move from today's world where the only people who can reprogram computers are the people who make the effort to actually learn the language of the computer, Fortran, Java, whatever it is. But maybe we'll be in a world in the next 5 years where computers learn the language of people well enough that each of us will become a programmer to the same degree that we can already instruct other humans. We already know how to do that, each of us. If we can instruct computers in a similar procedure, that'd be a game changer. We'd suddenly have billions of people on Earth who have the ability to reprogram their phones, for example. And combine this with that slide we saw earlier about language models being trained not just on natural language, but also on GitHub code. And those examples that we saw where the language model was attempting to translate natural language instructions into the equivalent Python code. So you put these two trends together, I think we really are in for, it is very plausible that in the coming decade, we're going to see a sea change in programmability, which would be a very liberating force for many non-computer science trained people. Okay, here's another one I have my eye on the clock, so don't worry. I'm going to make sure we have plenty of time for discussion. One of my favorites is what I'll call learning light bulbs. But if you look at the trends these days about the cost of hardware, in particular the commodity hardware that goes into cell phones, which are sensors, you know, like microphones and cameras and computation and internet connectivity, all these things that go into cell phones. We're producing those at such great scale now that the price of actually producing those is dropping rapidly. And so it seems that we're on the verge of being able to produce for on the order of 15, maybe 20 US dollars, light bulbs that have cell phone functionality. And so what does that mean? That means anywhere where you can plug in a light bulb today, in the future, maybe you'll plug in your learning light bulb, your AI light bulb. And what would it do? Why would we want this? Well, if we can, if we see some of these other technology trends that I was just talking about, including conversational learning, then this might be, these learning light bulbs might become the equivalent of the personal computer. Back in the 1980s, by the way, it was unclear whether personal computers were going to dominate the market, general purpose personal computers, or whether there would be a variety of specialized computers. Xerox PARC, for example. Xerox was producing specialized computers. IBM was producing the PC. In the end, the PC won out. And the reason it won out was the economics of producing commodity hardware were hard to compete with. Any specialized market just couldn't produce enough to bring the cost down. Plus, the technology development curve, Moore's law, led to the general purpose PCs doubling in power doubling in their capabilities every few years. And there was no way the specialized computers could duplicate that kind of development curve. But I think maybe the same, what will be the equivalent thing in AI? In AI, maybe it will be something like the learning light bulb that will be a general purpose AI device that can be installed anywhere. By the way, you won't have to worry about battery power anymore because it is a light bulb that's plugged into the wall. But then what will we use it for? Well, let's put one in each hospital room that has a patient in it. It'll use its cameras and its microphones to monitor what's going on in that patient room. It could be instructed the same way Toby's prototype system allowed you sometimes to instruct your phone. But for example, if you were the nurse, you could say to the light bulb in the patient's room, make sure that if the patient wakes up in the middle of the night, to let me know. And the light bulb would say, okay, and monitor the patient. Furthermore, if it had the right machine learning software in it, it could learn a sequence model. It could learn what's the next thing that's likely to happen in the room, what are the typical patterns, what are atypical. Usually if the patient gets up out of the bed and walks to the toilet, then they walk back and get back in bed, and they don't usually lie down on the floor in between. So you could imagine if you had a learning light bulb there that was also instructable by the hospital staff, could be pretty interesting. The same light bulb in your kitchen would instead help you cook dinner. The same light bulb in your coffee shop would learn to, for example, that typically when people get up and leave the table, they bring their purse with them and they bring their phone with them. They don't usually leave them on the table. And it could call out to you before you go out the door saying, hey, you left your purse on the table here. So the key question here is, will there be the AI equivalent of the PC? And if so, what will it be? I think it will, part of the question here is what will be the combination of sensors, effectors, connectivity, and can we come up with the right, can we be creative enough to come up with the software that will allow some generic device to be instructable and reusable in many places? Okay, maybe that's enough for now about technology trends. I want to end on social trends, and what I'm thinking is I want to end in 5 minutes, and I have quite a few slides on social impacts of AI, but let me just do it this way. I think there are really important social impacts of AI. I'm not the only one, most people think that. But let's go through a couple of them and see and talk through them. One of them is just bias in machine learning. People are rightly concerned about the potential for bias in machine learning. And unfortunately, bias is one of these words that actually has two quite different meanings in two communities. I'll distinguish them by saying socially biased, that we consider some decision procedure to be socially biased with respect to some input feature if the decisions output by that procedure are influenced by feature A. So for example, we could say, if the decision procedure D is one that approves loan applications, yes or no approve, classifier, and if A is the race of the applicant, then if D is different depending on the race of the applicant, then we could say it's socially biased with respect to race. Okay, that's a notion. The notion of statistical bias in machine learning is very different. Basically, we consider a machine learning algorithm to be statistically biased if it outputs decisions that are not the best fit to the data. To be more technical about it, we consider it biased if the expected value of the prediction differs from its true value in the data distribution. But in discussions of bias, it's important to think about these two different concepts and what really is the problem of bias in machine learning. In machine learning, it's really usually the problem is that the machine learning algorithm is designed to correctly reflect what's in the training data, but the training data itself is often socially biased. So for example, if we have a historical set of data that we're using to train a classifier to decide whether to approve a loan application or not, and if the historical data shows that more loans were approved for men and fewer for women, then if the machine learning algorithm is accurate or statistically unbiased, it will, of course, learn a classifier that continues that same social bias. And that's usually the big problem in bias in AI. Another kind of issue that happens sometimes is just that the data is not biased, but it's unrepresentative in the sense that it doesn't include a representative sample. So for example, there have been face recognition algorithms that were trained only on certain faces of certain races, and so they weren't very good at, for example, recognizing African faces. So these are some of the sources of bias in machine learning. In this case, there is some interesting technical work to try to address this issue. It doesn't fully solve the problem, but I think it's interesting and important. And the technical work in the area of bias, for example, includes changing the objective function that we train the machine learning system to optimize. For example, if we have data of loan approvals that's biased against women applicants, then we don't have to use the usual training objective function, which is, of course, the usual objective function in training a classifier is train the parameters of the classifier to maximize the number of training examples that are correctly classified. But given that we're trying to avoid giving more loans to men than women, if we want to avoid that, then we can change the objective to be the objective I just said plus a second term. And that second term can be a penalty for the difference between the ratio of men loans approved and the ratio of women loans approved. If we want those rates of approval for men and women to be equal, we can simply add that as another term in the objective function. And there's a variety of research going on of this type that basically is saying, let's be explicit about which biases we want to avoid. Let's build into the training objective of the machine learning system. Let's build in terms that prevent or penalize that kind of bias. And this is leading, I think, to a very interesting discussion, because now it turns out as this work is progressing, we're beginning to understand that we don't really know what we want. Do we want loans to be given equally to people of different genders, men and women, different races, different ages? Do we want no age discrimination? Income discrimination? Do we want income discrimination? Well, it is a loan, so the ability to repay the loan is a relevant variable. And so what we're finding is people are making more explicit what these biases are and have the ability to explicitly prevent them, is that it's leading to a much more in-depth and precise conversations about what kinds of biases are there and which ones are ones we want to build in the avoidance of. And at some point, for example, if you take the loan example, you can see that if you put too many constraints, you basically end up with a classifier that satisfies all the anti-bias restrictions, but cannot really stay in business because the loans it's giving are not being repaid. So I think the takeaway message there is that this noticing that bias is an important issue in AI and machine learning in particular has led to some technical approaches that can try to redress that problem, but that in turn has led to a very interesting and more precise conversation about biases and what we really want, and that's an ongoing discussion. Similarly, in the area of privacy, as opposed to bias, there are many issues, and again, there are technology solutions that are being developed to reduce the privacy impact of using big data in AI systems, techniques like homomorphic encryption, differential privacy, federated learning, which are effectively attempts to avoid collecting big data and then giving it out to people. And instead, many of the technologies that are being developed, federated learning, for example, are trying to leave the data distributed in place, for example, in each of our cell phones, but pass around the algorithm to do computations in each location, as opposed to bringing all the data together where the privacy issues can be more difficult to deal with. And again, that's a long story, and we're not going to have time to cover it here. But again, we see there is technology work to try to actually change the whole privacy value trade-off curve. There is a fundamental trade-off. For example, if you think of medical care, the more privacy you want, the worse medical care you're going to be able to get. The less privacy you want, the better care, but now you're sacrificing privacy. So there is this trade-off curve. And there is research going on to actually not just pick the right place on that curve, but to move the curve up by using encryption and federated learning and other things, so that we'll be able to achieve the same thing we used to achieve, but at lower privacy cost by using things like homomorphic encryption. Finally, I can't help mentioning another social issue is automation and the workforce and the future of jobs. This is an area where I happen to have spent some time the last several years. I co-chaired a U.S. National Academy study on automation in the workforce, and am currently ramping up to chair another study in this area for the National Academy. They're doing 5 years later another study. And there, what we found was that, yes, AI is, in some cases, automating tasks that humans used to do. In other cases, it's assisting humans. One key thing we found is that it's not the best way to think about automation of jobs is to recognize that most jobs are a bundle of tasks. For example, if you're a doctor, you have to diagnose the patient, you have to come up with the therapy, you have to have a heart-to-heart conversation with the patient about which therapy they want to use, what are the trade-offs. You have to bill the patient. Now, some of these tasks are amenable to computerization, billing the patient. Diagnosis, more and more, is becoming an area where the computer will assist the doctor, probably not replace them in the near term, maybe in some areas it will. But having the conversation with the patient is the kind of thing that I think patients will continue to want to have that conversation with their human doctor. So, like many jobs, being a doctor is actually a bundle of tasks. And if you actually look into the details of automation, what you see is that automation occurs at the task level, not at the job level. And so our conclusion about what's going to happen is that actually there won't be that many jobs being fully automated, except for single task jobs like toll booth operator. But most jobs which are multitask, what will happen is that AI will influence one or more of those tasks, maybe automated or maybe assist, as in the case of diagnosis for doctors. And what's going to happen is the job will reshape by redefining or reweighting the bundle of tasks that makes the job. Anyway, there's much to say there. But again, I think in this case, the takeaway is that society and us technology developers have a voice in how job automation is going to play out, partly because as technology developers, we can decide whether to develop a fully automated AI system or an AI system that has a human in the loop and tries to use the AI as an assistant in a human computer team that outperforms what either one could do alone. And, depending on the task, one solution or another might be better. But again, we're going to have a voice in how this plays out by choosing whether we focus on human-in-the-loop techniques or fully automated. Okay, so let me end there, because as I mentioned, I want to have time to have a very lively discussion with you. We've talked about a lot of these issues. To me, the takeaway is very simple. We live in one of the most interesting times in history. Certainly in the history of AI, this is by far the most interesting time. In earlier decades, AI was a fun laboratory curiosity, which was very interesting to discuss in philosophical discussions with your friends. But today, it's out here in the world with us. It's changing the world that we're in. The side effects, which some are intended, some are not intended, have raised issues around bias, privacy, automation of work, and more, democracy, fairness, and living in this very interesting age where AI is really reshaping to some degree our world, I think puts an opportunity and kind of a requirement on us as technology developers to be aware of these issues and to see how we can help. Part of what we can do to help is to educate our non-AI friends about what the technology really is, what it really can do and really can't do. And part of our job is to speculate, as I've tried to do here today, about the future and what might be coming, not guaranteeing that it's coming, but what might be coming, so that we can begin to consider and perhaps prepare for the other side effects of those future developments. So with that, let me stop and let's open it up to a discussion. Thank you.
Thank you so much, Tom. This is Amit Sharma from Microsoft Research. I think your talk really gave us a lot to think about, not just in terms of where AI is going, but also our role in it as technologists and people who are making these systems. So what I'll do is I'll just start with some audience questions. Maybe we'll start with the most popular question. 14 people have this question. So do you think the current approaches for representation learning suffice for real world applications? There's a large discussion around the need for neurosymbolic approaches or causality for robust predictions, which may be extremely important for real world scenarios. What has been your experience on these?
Great question. They do not suffice for what we really want to do. We're greedy, right? We want more intelligent systems than we have, and representations are really key to that. And I completely agree if people are suggesting that one of the big open problems in AI is how to bring together. There are two ways of phrasing this. One way is how to bring together background knowledge with new training data. A different way to phrase it is how to bring together symbolic and neural network representations. I think we need to do both of those. To me, one of the interesting questions about how this will occur is whether in the end it will all be neural. So let me just say this. My brain is completely neural. And so is yours. And it manipulates symbols just fine. So there's nothing in principle, seems to me, that would rule out that a neural system could manipulate symbols, since our brains do it. On the other hand, the current approaches that we have for neural networks don't come close to being able to do that. So I think it's a big mystery. One of the things I've been trying to track recently in this area is approaches people have been trying to use to bring background knowledge into neural networks. And for example, I saw a talk last month by William Cohen, who is now happens to be at Google, on using memories to augment transformer style models. And what was interesting to me about this is that the memory was storing, in this case, as you go through, as the language model was going through words in the sequence, whenever it would find a noun phrase, it would look it up in the memory to see what were all the mentions of this noun phrase in Wikipedia. But what that memory would return was not the symbolic text of the mentions, but the embedding, the neural encoding of those mentions. And those neural embeddings were trained so that it could simply add some, literally some, add that embedding to the representation that it had of the sentence at the time. So what he managed to do, the thing that seemed interesting to me there, is that here's a process, memory retrieval, which I think of as potentially a symbolic thing. We're trying to get background information about this word. But it managed to store in that memory something which was a neural encoding that was in fact devised so that it could be simply added into the neural encoding that was currently being used. So sorry for going into so much detail on this, but the reason I wanted to is that, to me, this is the kind of puzzle that we face right now. Will it turn out that we need graph style representations, explicit graphs together with neural networks? Or will it turn out that we'll find a way to translate those into neural encodings and go from there? I think it's one of the great open research questions.
No, that was good. I think it's good that you went into some details there. Another question that has come up is on the problems that we should be solving. So the question is about how does one reason about problems that can and should be solved with AI versus problems that sound like great applications, but may be problematic. So for example, predicting whether a person would commit a crime based on their photography or past evidence. But the questioner is asking, they used to think this was not very difficult to judge, but the possibility of superhuman perception makes it a little bit more difficult to think about.
It really does. A couple of comments. One, these are really social questions, not technical questions. These are questions, what do we want? Not what can we do? So I think as a technologist, I work on the question of what can we do? But the social question of what we want is at least as important in the end, but it's a distinct question. I agree that the ability to make these kind of predictions is likely to be greater in the future than it has been in the past. And furthermore, we have a choice about whether to do that. I'm not really sure what more to say about this particular case, except that a of a friend, Al Blumstein, who is a very well-known researcher on recidivism, people who are in jail and are let out of jail, do they commit another crime? And he points out that technology is a way of letting people out of jail safely. And so, for example, you put a tracking device on somebody, you can let them out of jail. In the old days, when we couldn't do that, we would keep them in jail just because. But now you can let them out of jail, and you can tell them, we will know if you go to this region of town, and we do not want you to go to this region of town. And so Al has sensitized me to the fact that technology can be used to, in this case, give people more freedom than they would have had. And so for me, that was an interesting idea. And this question makes me think of that. But I don't have the answer to that question.
Yeah, and it's a very hard question. And I'm glad we are having this discussion through the means of your talk. One question which two people asked was about AI augmented education that you mentioned. And they're just curious to know what are the sort of possibilities you see and what could be the future there.
Well, I'll try to keep this, shut me down if I get too carried away. 'Cause right now, this is actually one of my biggest passions. I think that the coming decade is the decade when AI can finally make a difference, especially in online education. I've been working with a company called CK12, which is a nonprofit company that offers online educational materials for kindergarten through 12th grade. There are actually quite a few people in India, quite a few students in India using this software, CK12. And they've had millions of students come and use their software, and so they have, here are the kinds of things that I think we can do. The low-hanging fruit, by which I mean maybe the first 5 years, is because we have these trajectories of students going through the curriculum at the level of keystroke recordings. So we know things like this student came through and they tried practice question 3, but they got it wrong. They answered B, the correct answer was C. Then they watched this video, but they didn't go all the way through. They shut down the video at 2 minutes and 30 seconds in. Then they read this paragraph. Then they answered this other question correctly. So we know sort of in the timings on all those. That's the kind of data we have. So from that, there are two things to try to do. One is, let's learn to predict the knowledge state of the student. That's not directly observable to us. We just get these signals from the things they've done. But if you think of there being a latent knowledge state of the student, we can try to estimate that from this data. And the way we represent the latent knowledge state is by a vector of 20,000 questions, and the probability for each of those 20,000 questions, the probability that the student will answer that question correctly if we ask them it right now. So that's how we represent the latent state. And of course, it's not fully observed, but we do observe them answering different questions, and we see what led up to that. And we see, so that's one thing, is trying to estimate the latent knowledge state of the student. The second is, second low-hanging fruit is what you might call the reinforcement learning problem. At any given point in the curriculum, there are several teaching actions we could take for this student. We could show them a video, give them practice question 43, show them a paragraph. While they're answering the question, we could give them a hint number 5, or no hint, whatever. We can give them motivating statements like, good answer, you got 10 in a row right now. We can do all those things. Those are teaching actions. And So the reinforcement learning question is, why can't we learn the right policy for choosing the optimal action at each point in time? And what do we mean by optimal? We mean we want to maximize the quiz score at the end of the session. So those are kind of, I think, the kinds of things that we can do. And the reason I'm so jazzed about this is that up until, again, this is the first decade where we've had enough data to do that. Up until recently, we never had systems that have been used by millions of students. But now that we do, there's just this opportunity to learn to teach better that we've never had. And by the way, a human teacher teaching for 100 years full time would never see as many students as these systems are seeing. So this, data-wise, this has the potential to turning into superhuman. It's certainly a superhuman experience base. Whether we can turn that into superhuman teaching competence remains to be seen. But those are the low-hanging fruit. Then beyond that, think about conversational systems. The CK12 system has a little chat bot on the side that you can ask questions to, and it can sometimes jump up and down and offer you hints and things like that. All the technology for conversational systems that is accelerating and advancing now at a rapid pace, that becomes available for these kind of systems. What about things that the student does off screen? One of the centers that I mentioned, these $20 million centers the US is funding, one of them at the University of Colorado is focusing explicitly on observing a table full of kids working together to solve problems, using cameras and microphones and doing eye gaze detection and trying to understand what kind of interventions with those kids, what kind of assistance, support with those kids could a computer partner, an AI partner, that's their phrase, who's sitting at the same table provide. So I think that the openings are huge, the potential is huge. And I'm glad to see there's this investment of funding in the US. I think worldwide this is, actually let me make a separate point. I think really important way to think about AI's impact on the world is that there are fundamentally two kinds of applications from a nationalistic perspective, say from the Indian perspective. There are applications where it's zero sum, where if one country does well, the other country does less well. Military applications of AI are the prototype example of that. If you use AI to improve your military, that makes the other countries relative to you fall. Zero sum. It's probably rational for countries to decide not to collaborate on zero sum applications. But there are other applications that are the opposite of zero sum. They're win-win. And education is one of them. If we can figure out technology to make teaching work better in India and in Belgium and in the US and in China, the whole world wins. There's nobody's harmed by that. And therefore, in these win-win applications, education, healthcare, climate, really the rational thing is to have much, much more international collaboration than we have now. And the people I speak with in government don't seem to get it, that there are these two very distinct kinds of applications. And we need to do some education of our politicians around that point.
Yeah, thanks,
Sorry, I got
Tom.
a different issue, but I think it's an important issue.
Yeah. I'm going to switch to Manik, who has a question.
Thank you, Amit. Tom, I wanted to go back to your comments on large language models, and I wanted to discuss the large in these large language models. Now, I'm not an NLP expert, so I wanted to get your thoughts on, is there something magical that happens, or is there a phase transition that happens that when these models cross a certain size, then they start achieving superhuman accuracy, say 1 billion parameters or 1 trillion parameters or whatever? And so does size really matter? And so is there a sense that, if we were able to train, let's say, a quadrillion parameter model one day on the entire corpus that the world has to offer, we'd get superhuman accuracy on a range of tasks? And then if the goal is to go larger and larger, what are the different ways in which people have explored this, right? Is it just to increase the number of parameters or the number of layers in the network, or what could be done over here?
Yeah, that's a great question. And I think the jury is out, but I think the current consensus in the papers that describe these large models from, OpenAI, from Google, from Facebook, the consensus seems to be that so far we have not hit the point of diminishing returns on scaling these up. That in fact, they test these models on a fairly diverse collection of test sets that involve things like question answering and sentiment detection and lots of other things. And so far, in the studies that have compared, let's say, the same architecture but with different size, the same basic transformer architecture but with more parameters, the empirical fact is that the more parameters, the better the empirical results. So that's one thing that seems pretty consistent across the papers from these different organizations. Another thing that seems really interesting, and GPT-3 was the first, the OpenAI model was the first to, I think, make this apparent, is that it seems that once you get to a certain scale, there's a way of, I'm searching for the right word to use, there's a way of, I'll say, teaching the model to do something new, which does not involve changing the parameters of the model. So for example, in GPT-3, you can teach it that you want to do analogy problems by giving it as the prompt that it's going to extrapolate. The prompt itself is a sequence of solved analogy problems, right? Like Earth is to the moon as the nucleus is to the electron, for example. And you would, if you give it a sequence of analogy problems like that, and then you start a new analogy problem but don't complete it, then it can predict the next word and it'll interpret it as an analogy problem, even though the model was trained not on analogy problems, but just kind of generically on text. So there seems to be this phenomena, which is really interesting and people are still trying to understand, around you can, by designing the right prompt, the right input sequence of tokens, you can basically get the system to do one task or another task. And you're doing it not by changing any of the parameter values in this 100 billion parameter model, but instead just changing the current state of activation of, internally in the network. So that's a phenomenon that I think is one of the most interesting and, to me, surprising abilities of these large language models. And so people now are using it, for example, to take the same model but have it either summarize this paragraph for a second grader, or the same model with a different prompt solve this analogy problem, or the same model with this other prompt solve this word problem about arithmetic. So it's crazy to me that you don't have to do, it's not like you're changing any of the parameters of the model to have it do these different tasks. You're just giving it a different sequence of input words to extrapolate. And that one seems to be below a certain size of model. People have not observed that being as effective. So that one, I think, is one of the interesting open questions. But the other thing I'll say is, it also seems to be obvious, but with these models, I've stopped saying obvious because they keep surprising me. But it seems to be obvious that there are certain capabilities these models don't have because they just don't have, for example, if you stop me right now and you say, Tom, what are you doing? I'm going to say, I'm answering this question about scale of language models. Why are you doing it? Well, I'm doing it because I'm in the middle of giving it, I'm at the end of giving a talk and we're in the discussion period. I think those kinds of capabilities that you and I have intuitively, I don't see how they come out of larger scale systems with the same architecture that these models have. But I've been surprised in the past. I'm curious what you think about that.
I have lots of thoughts, but I don't want to bore everyone with them. I'd love to continue this discussion with you offline, so I'll mail you. But I think for now, Partha had some questions as well, so I'll hand it over to him.
Okay, thanks.
Yeah, thanks, Manik. Hi, Tom. Thanks for a great and thought-provoking talk as always. Yeah, so I I guess like with all of these remarkable advances in language modeling, we have started to see these kind of like transfer learning effects where at least for supervised problems, we are able to cut down on the amount of supervision that's needed. But in order to make that happen, you still need like good language model core. And primarily the models that have been built are all from the web data, be it web pages, conversations, code type of data. But one thing I worry about is that for a lot of the languages and communities around the world, they don't have good representation on the web. And maybe we don't have like a economically viable way to create such large data sets in short span of time where these current techniques could adapt and be more inclusive. So I'm just kind of like thinking whether these data sets themselves are will take us a long way, but maybe we need to go beyond that and think about maybe how we can do more participatory model building where it's kind of like some part of it developed with available data, but the other ones where we don't have for certain communities, how human in the loop or people could participate even in the pre-training stage. So just was curious about your thoughts on how we can be more inclusive towards building these language models for underrepresented groups. Thank you.
Yeah, really interesting thought. First of all, I'll say I was looking at the data that was used to train the most recent Google model, the Palm model. 4% of that data was Wikipedia. It was international Wikipedia. I think it was all of international Wikipedia, but it amounted to only 4% of the data. 50% of the data used to train Palm was social media data. Just think about that. But I think your point, your thought, your question is really on target. What does this mean for low resource languages? I like your thought that maybe one way to do this is to actually have a more participatory process that allows people with different languages to interact with the system and in that way teach it more, maybe even explicitly teach it. But I'm also thinking about that example that I gave way at the beginning of the talk about the computer vision transfer, where a model trained on normal photographs of our surroundings ended up being so useful for training a very different language of images, which was skin cancer detection. And that the success of that example in computer vision makes me wonder if there could be a similar analogous situation here in the world of language. What if it turns out that part of what is being learned by these large language models is just the structure of reasoning, the structure of representations of things that we discuss in all languages, you know? And what if, again, an analogy to that computer vision thing, we can therefore get away with a relatively smaller amount of specialized surface level form language, and piggyback on that very foundational representation that was learned from a different language. So I think that's kind of an interesting open question that goes along with your thought.
Yeah, makes sense. Thanks, Tom.
I'd like to actually take this chance to say there were over 40 questions in the chat, so thank you, everyone. We had almost 400 participants at the peak, so very vibrant conversation. Tom, we can email you those additional questions.
I'd love to.
And thank you very much. It was a tremendously enriching session, and thank you so much for being here. If we're doing one more, maybe I could ask Tom. You know, you gave many examples where AI is now deceiving us, tricking us into thinking that a human has done something, has generated text, or, you know, we see online deepfake videos and other things that look to be real but actually are not real. What are your thoughts on the long-term implications for truth and knowledge in the world? You know, can AI also help us to authenticate real knowledge and to help distinguish real from, you know, artificial things in the world? Or will it ultimately be, you know, more powerful as a tool for misinformation, perhaps, in the future?
Wow, you asked the most difficult question. I have to honestly say this is one of my biggest fears for AI, because I think the potential for using it for disinformation and for participating in social media with an agenda is huge, and it's not good. But I think the potential is there, and I think there are organizations in the world that would like to use that kind of technique. So for me, this is one of the frightening future issues, and I would love to see even more research on trying to understand how to deal with and reduce that risk. But I have to be honest, I think for me this is one of the biggest risks, and I don't see a solution. I hope there is one. I hope one of you sees it.
Well, thank you. On that hopeful note, Tom, I think we will probably close. Thank you so much again to you and all of the organizers and all of the many attendees that we have. Really enriching and fruitful discussion today. So thank you so much.
Hey, thank you, and I really appreciate the discussion. And it's great to see a couple of familiar faces too on the screen here. So hope to see you all in person before too long.
Absolutely. Thanks, everyone.
Thanks, everyone. Thank you. Bye-bye.